Hello everyone, welcome to this TOPIQ webinar on Pump-multiprobe Photocrystallography. Thank you for joining us today. Before we start, I'd just like to make a few announcements and then pass over to my co-host to make an introduction. So firstly, we will be recording this webinar, which you can see is happening in the toolbar. Recordings will be made available on our website, so if you want to find the recording after the fact, please visit this URL to find it. Throughout the course of the webinar, please do feel free to ask questions. We'll collect them and ask them directly at the end in the live Q&A. If there are any questions left over that we've not been able to cover in the time we have, then we'll try to answer those by email or some other means. Just a reminder, please do join our X-ray forum. It's where we highlight things like this are happening, and if you want to find out about future events, then it is a good place to find those. And speaking of future events, I just wanted to draw your attention to our next webinar, which will be on the 7th of March, and the topic will be high pressure crystallography. So if that's of interest to you, then please do register. You can use the link here, which I appreciate is a little bit long to type in quickly. So I've put this QR code here for you to use. And I will pass the floor to my new colleague, Joshua Morris, who has joined us as the sales manager for, well, I'll let Josh introduce himself and he can tell you a bit about himself before he introduces Lauren. Okay, Josh.
Cheers, that, Fraser. So just hi, everyone. So I'll just start quickly introduce myself. I'm the new sales manager for single crystal at Rigaku, taking over from James Gordon, who I'm sure the majority of you met already, as he moves over to Rigaku in America. I've moved into this role pretty much directly from my PhD that, interesting enough, was actually supervised by Dr. Lauren Hatcher, who is our invited speaker for the TOPIQ webinar today. So Lauren's research is focused primarily on the investigation, looking at the structure-function relationships in switchable materials and looking to understand the key structural influences that impact their functionality. So Lauren's group is using primarily in-situ crystallographic techniques, in particular photocrystallographic techniques, to study these switchable materials in real time. And from that generate molecular movies to actually follow and track these 3D crystal structures over time and look at the photo-induced changes. So as I'm sure a lot of you know, these kind of pump probe experiments previously quite limited really to synchrotron sources, but with the new advancements in X-ray generation, the increased flux available and the increase in detector science, it's now possible to conduct these microsecond scale time resolved experiments now in the home lab. So yeah, I'll now hand over to Lauren for what I'm sure is going to be a very interesting talk.
Thank you very much, Josh, for that very nice introduction. And it's nice to see Josh kind of moving into his new role as well, which is very exciting. So for those of you who don't know me, as Josh just said, my name's Lauren, and I'm a university research fellow, Royal Society funded university research fellow at Cardiff University. So as Josh has said, I'm going to tell you a little bit about our developments of time-resolved crystallography studies using our new XtaLAB Synergy-R system at Cardiff. So I can make this hop along. Is it going to do it? There we go. So just a brief summary of what I'm going to talk about today. So first of all, I'm going to talk a little bit about the background to these studies and the motivation that comes, as Josh rightly said, from synchrotron studies over a number of previous years. Then I'm going to talk about the instrument we've been developing with Rigaku, a little bit about what's actually involved in there. And then in the third part, going to talk about some of the commissioning experiments we've done. And then I'm just going to finish up with talking about where we see this work going in the future as well. So first of all, to talk about that motivation. So photocrystallography is an area of crystallographic research that's really been developed since the late 1990s. It was kind of pioneered by Philip Coppens in America in the late 1990s. And he said that photocrystallography was the study of light-induced processes in crystalline materials using X-ray diffraction techniques. So it obviously involves us doing in situ irradiation of our single crystals whilst they're in place on the diffractometer. And we use that to watch the photo-induced changes happen in our crystals in 3 dimensions. So it requires a small but still quite a significant structural rearrangement, because it's got to be small enough that it can be transformed in a single crystal to single crystal fashion, typically, but also large enough that we're going to see the rearrangement of the electron density. So we'll see it by crystallographic methods throughout the bulk crystal. And there are many examples of systems that we've studied that are both irreversible and reversible type photo reactions in crystals as well. So one of the major things is that we need to be able to irradiate the crystal in situ on the diffractometer. So in the early days, people used lamps to do this. But people also have used lasers, sort of the complete other end of the technological spectrum, actually hitting crystals with very high power lasers as well. More recently, in the last sort of 15 years or so, LEDs have become more and more commonly used. And this is something that we do in our group. And we develop bespoke LED arrays that can usually sit on the neck of the cryostream or sometimes be mounted in other ways. And they're often curved, kind of an arc shape, like you can see in this picture here. I'll just find myself a pointer if I can. Might be more helpful, mightn't it, pointer? There we go. So I have my laser pointer. So this is an older design now, but it sits basically in an arc around the crystal position. It's mounted on the cryostream. And that enables us to maximize the light penetration all around the crystal position, but it also has gaps to enable the collection of the full X-ray, single crystal X-ray data at the same time. So we tend to categorize photocrystallography experiments in terms of the time scales of the study that we're doing. So at the very slow end of the scale, we have so-called steady state methods, where essentially we are looking at lifetimes often that are for anything from hours up to infinite, particularly often systems that are cryo-trapped. So we often use the cryostream in order to make our excited state essentially infinitely lived for these experiments. And that means we can study them using a standard X-ray diffraction experiment. And we'll talk a little bit more about that in just a second. In the middle, we have so-called pseudo-steady state methods, where we essentially keep pumping our excited state up into some kind of equilibrium state by continually, so in my diagram, I've got a pulsed light source that will continue hitting it. You could equally do this with a continuous wave source as well. And then at some stage, once you've reached an equilibrium position in your excited state, you then start doing a data collection with the irradiation staying on in situ. That can be useful for lifetimes a little bit shorter than the timescale of your experiment. So things for anything from minutes and seconds down to several hundred milliseconds. And then you have fully pump probe methods, where essentially you have a pulsed light source, so usually a pulsed laser, and you synchronize that with some kind of pulsed X-ray source or gated detector. We'll talk a bit more about that in a second. And essentially you can then vary this time delay between the light pump and the X-ray probe to be able to probe your excited state at various points in the decay process. Okay, so as I said, we'll start at the slow end of the scale and talk briefly about steady state photocrystallography. This, as I said, is suitable for irreversible cryotrap processes, long-lived processes. And the lifetime of that excited state needs to be kept such that it is longer than the time scale of the diffraction experiment in order for you to see something in that second experiment. So we first of all, we get a ground state. So that's our first little hit of X-rays here. We get a ground state structure in the absence of any light. We then irradiate the crystal for a time period, and you have a sort of an induction point, and then you reach your excited state, which should be stable. And then once you switch the light off, because it's got a very long-lived excited state, it should be stable long enough for you to take a second standard X-ray diffraction experiment, which should contain your excited state data. So ground state and photoexcited state data is collected. What we tend to do is develop something that's called a photo difference map. Again, we'll talk a little bit about this later, but that's made between the ground state model and the excited state data. And you can see new peaks in that difference density map that correspond to your excited state. Okay, so we've been doing this, these sort of experiments for a number of years now, both in my group and in the research groups that I've worked in the past as a postdoc and a PhD student. This is our LED ring, which you saw in the previous slide. We've got a number of updated designs on this nowadays, but this is the original one. And as I said, we've got kind of gaps for the diffraction to come in and gaps for them to go out as well. Okay, so at the other end of the scale, then we've got these pump probe methods, which, as we said, they're a fully time-resolved approach to photocrystallography. And here we need our pulse light source. So it's typically a laser. Certainly traditionally has been a laser in the past. And then we need to synchronize that with the data collection. Okay, so originally you needed to generate an X-ray pulse. And this was first done mechanically, for example, by using an X-ray chopper, so physically breaking up the beam by putting some rotating metal in the way. Okay, but nowadays, with the advent of fast readout detectors, such as the HiPix detectors, the Rigaku systems that we have, we can simply electronically gate the detector response, okay, so that we're only recording for the period that we want it to be, okay, or only bin the data that we want to see, okay. So for all of these methods, though, one of the biggest challenges is to be able to synchronize the light pump and the probe, either the X-ray pulse or the detector response, in order to achieve that required time resolution repeatedly over and over across many cycles. So just a quick aside then, I'm going to talk in a minute about kind of the background benchmarking experiments we've done at synchrotrons to kind of develop these techniques. And these are primarily done on a type of molecular photoswitch that our group knows an awful lot about, and those are solid-state linkage isomer switches. So I apologize to anyone on here who's not really a chemist, but I'll try and keep this quite accessible. But essentially, solid-state linkage isomers tend to be metal or organometallic complexes where you have an ambidentate ligand bound to a metal center. And that ambidentate ligand can be made to switch its mode of binding to a transition metal center through one or more different donor atoms. So we have things like metal nitrosyls, where they could switch from an N-bound to an O-bound, or even a side-on linkage isomer with irradiation with light. Or what we're particularly going to talk about today are metal nitrite systems, where we go from an N-bound nitro, that's the word I'm looking for, N-bound nitro ground state to an O-bound nitrito. You can either get an endoform or an exoform when you irradiate the crystal with light. So switching, as I say, can be achieved with light. It also can sometimes be achieved thermally with these systems as well, but we're particularly talking about photo switches today. And that we can achieve very long-lived metastable states by cryotrapping those excited states at low temperature. So we can study them with the pseudo-steady state, the slow experiments. But it also turns out that their excited states are very highly temperature dependent. And so if you do these experiments, these photocrystalography experiments at high temperatures, you can actually start to see dynamic decay in these systems, and you can follow it with pump probe studies. The reason they've been of interest in the past is that those atomic arrangements at the atomic scale are accompanied by bulk property changes in the bulk crystal. So things like color switching, particularly switching of refractive index, has proved very useful for applications in the past. So that was a little aside. But essentially, if we irradiate these crystals, what we see is we start in our N-bound ground state, and if we irradiate for a period with an LED, we eventually see conversion to and in this case, a fully 100% excited endonitrito linkage isomer. And this one actually happens reasonably quickly. The whole bulk crystal can be converted in under 15 minutes generally. At 100 Kelvin, and that state stays cryotrapped until around about 200 Kelvin, when we begin to see dynamic decay back to the ground state. And as I say, the excited state is very temperature dependent. So if we control the temperature, we can actually control the lifetime of the excited state. So because we realized this, we went ahead in about 2018 and developed some photocrystallographic kinetic experiments that were designed to follow the forwards photoexcitation and reverse thermal processes with time and temperature. So for the excitation, what we've got going on here is we collected series of experiments where we irradiated for a period, we stopped, and we were at a temperature here, you can see below 200 Kelvin, so where the system will be cryotrapped. So we irradiated for a period, we stopped, we collected a data set, we moved on, irradiated again, stopped, and in the end, we build up these excitation profiles where the crystal isn't decaying back. Okay, but to understand the decay, we need to go a little bit higher to where the system begins to dynamically decay on a time scale that is observable just about with a standard steady state, standard X-ray experiment on a normal diffractometer. And we were able to then follow the decay dynamically at temperatures between about 210 and 230 Kelvin and get an idea of these decay profiles. So what you can see is that these data points have been fitted. They're not just lines drawing the data points, they have actually been fitted with a solid state kinetic model, which is based on a nucleation and growth method known as JMAC theory. And essentially by fitting these data, what it allows us to do is extract some kinetic parameters from these data, most particularly a reaction rate constant K. This is a reasonably accepted solid state model for these kind of transformations in crystals that's been used by a number of others, not just us. So in developing these kinetic studies, I think if it moves on, we can combine basically our JMAC expression with the Arrhenius expression, and we can begin to get an expression for the half-life, which gives us an idea of the lifetime of the excited state at these temperatures. And we can even begin to extrapolate up above room temperature and start to think about what kind of lifetimes we're going to see in this system at what temperature. This actually allowed a colleague of mine, Dr. Jonathan Skelton, who's now at the University of Manchester, to develop me a numerical simulation tool based on these kinetic experiments at low temperature that is able to predict how those linkage isomer ratios evolve under different experiment conditions. So it takes as its input the kinetic parameters from those low temperature studies, and it spits out predictions on all sorts of things that you ask it. But most interestingly, you can get it to predict you the kind of conditions you might need for a pump probe experiment at a given time scale. Okay, so we'll see a little bit more about this in a minute, but this is now allowing us to actually design our pump probe time resolved experiments by using primarily just single crystal data. You could do this with spectroscopy, and a lot of people tend to do that in the past, try and get spectroscopic data of their crystals and then use that to guide their pump probe experiment. It can be difficult though to keep the same kind of conditions because you have a different temperature control and all these things. So if you can do it on the same diffractometer as you're going to do the time resolved experiment on, it can be really quite powerful in predicting what you need to do. So we then went on to think about how we were going to irradiate these crystals for pump probe experiments. So I've said previously that people tend to use pulsed lasers for this. There can be a number of problems with that. Primarily, the lasers tend to damage the crystals quite significantly, and also quite often tend to heat up the crystals quite significantly, which affects the excited state lifetime that you see. So we decided to try and use LEDs to do this in a pulsed manner. Okay, because we can actually get LEDs now that can be pulsed down to relatively quick timescales, certainly over a second or a few hundred milliseconds. And the LED setup gives us something that lasers actually make quite difficult. We have complete flexible control of our complete excitation and decay profile for our pump probe studies. So with a laser, you're very much fixed to probably a particular pulse width of your laser, or a few particular pulse widths, depending on how expensive your laser is. You're probably also fixed to a certain cycle time, depending on the rep rate that your laser is able to operate at. So if we're using LEDs and electronic control, we have complete flexibility over what we want to do with this. So that's quite attractive. And we can try and optimize the excitation period and the decay period in order to see a maximum excited state occupancy in these experiments. We also realized we had an opportunity to redesign the experiment somewhat here. So traditionally in a pump probe experiment, you'd collect one time delay, you'd do a single time delay for each pump probe measurement, and then you'd shift the time delay between the light pump and the X-ray probe a little bit over, and you collect a second whole data collection. And in that way, you'd take maybe 5, maybe even 10 data sets in order to build up your decay profile and understand what's happening in your structure as it decays. So for these LED pump X-ray multi-probe methodologies that we've developed, we're kind of leveraging both the flexibility of the LED setup and also that high frame rate detector. And we can actually collect all of the time delays in one single collection now. And so we went forward and we benchmarked this idea at Diamond Light Source using that same palladium nitro system that I introduced to you earlier. We used that numerical simulation tool to predict the ideal parameters. And we did this proof of concept study where we looked at time resolutions between 8 seconds and 400 milliseconds. And these are the results that we see. So we can see that as we raise the temperature, we get faster decay, which is what we expect. We can see that we get the kind of excited state we expect, and we're actually able to generate these sort of molecular movies, if you like, of the excitation and decay process, where we can watch so what we're watching here is difference density. So the green things are coming in now is the excitation period, and then you see it decaying away again as we turn the lights off and we let the system decay. There's also something interesting potentially going on around the metal as well, as if the metal is either moving or possibly the orbitals are changing. That's a little bit more qualitative, but it's an interesting outcome of being able to look at 3D molecular movies from time result studies as well. Okay. So what are the data collection limitations from that study? Primarily, as Josh said at the beginning, we needed to use, at the time we did this, we needed to use synchrotrons to do these experiments. But actually not every aspect of the experiment is well suited to using a synchrotron. So most particularly, you have these strict time limitations on your beam time. You know, you apply for a certain amount of time, you go and you do your experiment, and that's all you get. So that really isn't conducive to kind of problem solving and also developing different kind of experimental protocols and really trying to understand the setup and the equipment that you're using can make it quite challenging and very high pressured. Also, the beamline is kind of very multi-user and it's under constant development. So we found whenever we went back to do repeated experiments, things had changed, and that was quite challenging as well. And we also find that with a lot of our crystals, the synchrotron beam is too intense and it does damage them as well. So what's the solution? Was to try and create a lab-based diffractometer. And that, after all that preamble, that's really what I'm here to talk to you about in this webinar today. So let's talk about the instrument that we've been developing. So we have it's a Rigaku Synergy-R system. And essentially, the grant that we got to do this, we named it the TRIC system, the time-resolved instrument for X-ray structures. And essentially, it's, to all intents and purposes, hardware purposes, it's largely a standard Synergy-R system, except with a few little tweaks. So we have this sort of bespoke firmware upgrade in the goniometer, because the goniometer needs to do some special motions that we'll talk about when we talk about how we collect the data. And it also needs to synchronize to its movement to the detector and to our light source as well. So there's a little bespoke upgrade in there, several firmware upgrades. We've also actually, much to some of the engineers discussed, we've engineered back in the fast shutter that used to be there, because obviously for most people who know about these high-pix detectors, these HPC detectors, so we tend to run in shutterless mode now, whereas on an old CCD system, we would have an old fast shutter that opened and closed when we were collecting data. We've actually got the fast shutter back in, because when we irradiate the crystal, we want to protect it from the X-rays as well. Then we've got a standard liquid nitrogen flow device, so we can control the temperature. And you can see it isn't actually, I apologize, it's not the one in the picture that I could find. We've got a high-pix 600 HE, not the arc that's in this picture here. And then obviously we have an R system, we have a rotating anode to have lots of nice flux for our very short time resolution that we're trying to achieve. We then put our illumination setup in. So these are either LEDs, or we are looking at using laser diodes as well at the moment. And there is the potential to upgrade to have different sample environments as well in the future. That's not something that I'm going to talk about today, but we have that potential capability in the future as well. So how does everything talk to one another? Well, essentially, we have an output TTL trigger signal from the high-pix. And the LEDs are connected to that and to a lab power supply via an Adafruit driver. Okay, and so it's all quite simple, quite cheap electronics, and all that powers the LED array in response to the TTL signal. The Raspberry Pi Pico that's in there, that which is here, that acts as the waveform generator, so we get the correct pulse shape. And then we have everything hooked up to an oscilloscope so that we can see what the output's doing and check it's doing what we expect. All this looks a bit like this under the hood. My postdoc Ben's very good at making things neat, and so it's got a nice little cover over it, 3D printed cover over it, and that's all actually magnetized to the side of the diffractometer. So how do we set up the experiments? So I very much have to thank Matthias and his team for developing all this for us. This is very much their creation, not mine. But essentially, under other experiments on my system, at least, because we're still in the discovery phase, I have this photocrystallography option down here. I can drop down to photocrystallography. And that brings up this experiment dialog where we start to put in all of the parameters we want for our excited state experiment. So we set the excitation time, the pump time, and the decay time, which we might call the observation time in this software. So you can see what we're doing here is we're irradiating for 5 seconds and decaying for 2. And then we set the slice time, which basically tells us, basically dictates our time resolution. So we've got a slice time here of 200 milliseconds. What's actually happening is that we're trying to take an overall image width of 0.5 degree, either in omega or phi, so very much like a standard X-ray data collection. But what we're actually doing is we're collecting, in this case, 10 lots of static images every 0.05 degrees. And we're later going to, we split that up into time bins. We later recombine those into 0.5 degree wedges, where they basically look like a very standard laboratory data set that you might take, but they've actually then been split up into all the time bins as well. And I'll describe a little bit better what that means in just a second. But yeah, that essentially means we have 10 times 0.05 images that are piled up to generate a nice, still very thin slice omega stand with nice good statistics. So, sampling the rocking curve of each refraction nicely as we go along. And then we set up the strategy very much like you would do for a normal experiment. We try to collect as many frames as we need in order to get a complete data set. So I'll play a little video that shows this in action. So what you can see here is that we're looking at down the microscope camera here. You can see the lights on and the lights off. Not very well tuned in, but the oscilloscope is marking up where we get the trigger signal and the LEDs on. So as this comes back on now, we get a bump on the oscilloscope, and this is doing 10 times pile up, and then we get a frame recorded within Chrysalis Pro. So I'll show you how this works a bit more pictorially, and I really have to thank Prishamek for developing this for me, to make it understandable for everybody. But basically, what we do is that if we consider we have n number of time bins, so from T0 all the way up to Tn, at each goniometer position, we move to a position, it then collects n number of static slices in shuttleless mode for a period equal to that observation time. So that tends to be the decay time. So we're watching the decay of the process here as it goes along. Those are then piled up into n different buffers, which is what these different colors represent. And so they're held in different buffers according to their position in the image sequence. And the goniometer then moves forward, usually by 0.05 degrees. Okay, and we collect another n number of static slices at that position, which are saved in the buffers again. And we keep going, we keep moving forward with the goniometer in either phi or omega, until we've moved through the total frame width, that 0.5 degree scan that we're aiming for. And then each of those n buffers is then summed together, okay? And then they're dropped into their corresponding data collection folders as a frame. Yeah, so they sum up to be a 0.5 degree scan, and that's each frame, but they're already separated in buffers, and so they drop into each of the folders for each of the different time delays. So what we end up with is a set of standard crystallist profiles for each data set at each time point that we've set at the beginning of the experiment. Okay, so that's essentially what I'm saying here. So we get frames, and as the crystal moves around, we keep collecting those up just like a normal data collection. Okay, so that's essentially what I've just said on the slide. So we then basically take our standard set of files in each of those folders with the different time delays, and we process it as normal, usually using the Profit batch processing in order to automate stuff as much as possible, because you really can end up with an awful lot of data to process under these kind of experiments. So that was the instrument. So now I'll talk a little bit about a few commissioning experiments we've done with this. So the first ones were just very straightforward data quality tests. So these were control experiments where we're basically running at room temperature with the ILID crystal, just as a standard, and no illumination, just so we can assess the kind of the data quality coming out at some of the lower time resolutions that we might want to look at. So you can see we've got a pump time here, nominal pump time of 0.1 seconds. Really, we haven't got any LEDs in there or any light at all. So this is just to prove that it's working and look at the triggers. Then we've got an observation time of 170 milliseconds. And we're going to split that into 6 sample sets, 6 bits of time resolution. So we have a time resolution of 28.7 milliseconds. Okay, so what did we see? Well, so this is our first time point, and you can see we've got rather nice data, despite the fact that this is only very short exposure. Okay, if we process all the data, all 6 of those different time delays, you see we've got really very comparable data going on here. Nothing really that isn't within error. And we're happy we've got some really nice data quality here. So this all confirms that we can get some really nice standard experiment data at millisecond time resolution from the equipment. Then we went on to try and put lights in and a photo switchable crystal and see if we could basically basically achieve the same kind of results as we saw at the synchrotron. So we're benchmarking with that same palladium nitride linkage isomer switch. And we used the numerical simulation tool first, as I said in the previous experiment. So we did those slower experiments first on the system, where we get all of our input kinetics. We look at the excitation and the decay kinetics. We get our rate constants, and we plug those into the numerical simulation tool. And what we get output is this text prediction. We tell it some cycle times we'd like to do, and it tells us how long we should irradiate for and how long we should decay for and what temperatures we might like to set the cryostream to be. So what you can see is that for these linkage isomers, they really work on a kind of the second time scale, which is a shame because we quite like to go faster, but for benchmarking purposes, this is fine. So at longer excitation times, we see more excitation. It's a bit easier to see. If we go as short as 2 seconds, we're really looking at very minimal changes. And that is a challenge in itself that we'll talk about a bit towards the end of the talk in a few minutes. But this gave us something to work with. So the very first thing we tried was to go to 265 Kelvin. We tried a cycle time of 18 seconds, an excitation time of 10 seconds with the LEDs, and then we watched the decay for 8 seconds, and we sliced that in 500 millisecond chunks. Okay, and what we saw to begin with is some really nice data, some really nice diffraction. When I came back a few hours later, the diffraction had dropped off a little bit, and when I came back after a day or so, it dropped off rather a lot. And what we can see here, so we look at a crystal that hasn't been irradiated and a crystal that has, we've got some crystal damage. And it turns out this is actually not the result of X-ray exposure. This is totally the result of light exposure with the LEDs. Even though these LEDs aren't fantastically bright, this system does get photo bleach with extended light exposure. Okay, so this is a problem that we need to think about overcoming. What we could do with the data we had, though, is to look at an individual reflection and try and get a feeling for whether we were seeing excited state and decay during this experiment. So what we can see is that we know from prior work that the 210 reflection actually changes its intensity relative to the linkage isomerism process. So it increases with irradiation, its intensity, and it decreases as the sample decays back to the ground state. So you can see that we basically went and picked out the frame with the 210 on there, and we were able to integrate over that peak. And you do see the expected trend. We're seeing some decay, albeit with a bit of noise going on. So this was encouraging that we were actually seeing the right things happening. We just have to be able to get a handle on helping our crystals to live. Okay, so what's the solution? Krishmek and the team, they looked at reducing the number of pileups for me, which essentially is going to reduce down the amount of light exposure on the crystals. So we now have the ability to vary the number of slices, the number of pileups that we do, somewhere between 4 and 20, which then influences the minimum slice width and hence the data quality. But a nice compromise is rather than having 0.05 degree movements that add up to a 0.5 degree wedge, we can now do 0.1 degrees that add up to a 0.5 degree wedge. So we're having 5 pileups and not 10. So we've actually halved the amount of light exposure on the crystal, which is going to help it live much better. So we did this, exactly that. We tinkered with the conditions slightly, ever such a slightly higher temperature, slightly longer decay time. And what we see is that our crystal lived. First and foremost, we got complete data sets. So these are now conversion fractions, percentage excitations that have been refined from a full single crystal data set at each time point. And what you can see is that we do indeed start to see some decay. So we start off with some excitation up here, and we immediately see it decay as we go forward in time, which is really nice. These error bars are a standard deviation that I took from doing a dark state run with the same crystal with just the X-rays, and where we saw essentially no change, and I just generated standard deviations from that. So we can see decay, so that's really exciting. That's comparable to the synchrotron. What we also see though is we look slightly longer, we see a bit of variation as we go on in time, where essentially everything should be still staying quite steady. That's all within error, but what I think it's telling us is that we're not doing such a good job of refining the lower excited state occupancies once stuff's starting to decay. It's not decaying to nothing essentially. So there could be a couple of reasons for this. It's possible this is because there's some X-ray excitation in these crystals. We do see this with the linkage isomers to a small amount. So we're talking about 4 or 5%. It's possible that's like the baseline that we're working with. Or it's a function of our processing protocols, which seems perhaps more likely. And essentially, we need to think about how we're processing these data. At the moment, we're using just a very standard processing with ShellX and using a disorder model and part instructions just on the data as it is. And when we're looking at very small changes, maybe this is no longer the best way of looking at this data. So future developments, how can we improve on that data processing? The way that sticks out to me is that we consider using some kind of difference method. The very straightforward one, the very visual one, is to use the photo difference maps that we talked about earlier, where essentially we import the ground state coordinates and refine them as a rigid body against the excited state. And then we see in the difference map the peaks corresponding to our excited state. So we're not biasing our results by imposing any kind of crystallographic model on there. We're just looking at the difference density compared to the ground state and saying, is there excited state, yes or no, and roughly how much it is. The problem with that is it's qualitative, but not particularly quantitative. And so we still probably want to be able to refine a data set at the same time. Another way to do this borrows from some of the previous work by the Coppins group back in the late 2010s, where they do something essentially akin to a difference map in a spectroscopic study. And they generate something called response ratios using this formula here, and then they refine against this ratio between the excited state and the ground state data rather than refining on the raw measurements themselves. And the idea is that this helps you to see small changes because it's going to maximize the differences between your ground and excited state rather than just looking for teeny tiny amounts of excitation in the raw data. Okay, so we haven't done this yet. This is something I'd like to look into in the very near future. Future materials to study as well. So we aim to study a much wider range of compounds now. We're happy that we've got something we can work with, and we'd really like to test the performance over a few tens of milliseconds, tens to hundreds of milliseconds rather than on the second scale. So there are things like luminescent, this is a luminescent silver compound that has a POP anion and a phenanthaline, sorry, POP ligand and a phenanthaline ligand. It has quite a long luminescence lifetime, even at room temperature, that's in the right kind of region. So we'd like to look at this. These are actually, in fact, Josh's compounds, who introduced me from his PhD. These are pyroelectric switches that you basically see order-disorder transitions in these materials. They're also linkage isomers as well. So we'd like to look at this in a bit more detail with time resolved. And we'd also like to potentially think of other materials, spin crossover switches, metal organic frameworks. And we are working with biologists as well, in collaboration with biologists, to try and do some well-diffracting photoactive proteins too. So please get in contact with me if you think you have materials that could be applicable for study with this system. We'd be very happy to hear from you. One last thing to leave you with, some development that's coming up in the next couple of months, is we're about to get to receive an inline Raman probe to put on the instrument as well. That's from a Royal Society research grant, and basically that's going to allow us to have simultaneous collection of crystallographic and chemical information on the photo switching dynamics in real time. That has, I think, the potential for very high impact papers. So again, if you have materials that you think would benefit from having that, we'd be very happy to talk to you too. Okay, that was me. So I just want to say thank you to everyone that's been involved in the work. So my group members, past and present, most particularly to the Rigaku team members. So that's Mateus and Prismek and Martin as well, who have helped develop the software. Collaborators, so my previous supervisor, Paul Wraithby, and his group at Bath, where a lot of the early work at the synchrotrons was done with Mark Warren as well at Diamond Light Source. But most particularly, thank you all for listening, and I'm very happy to take any questions.